Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
String theory suggests that the universe is not made of particles, but of tiny, vibrating strings of energy, harmonizing to create all reality.
Hey there, and welcome to This Explainer. Think of me as your friendly tour guide for the next few minutes. Today, we're going to take the incredibly dense, highly complex taxonomy of modern theoretical physics and organize it into a clear, navigable map. We're going to look at the structural categories, the mathematical rules, and the fundamental objects that represent humanity's ultimate attempt to read the very source code of reality.
Here's our roadmap for today. We'll start with the fundamental objects, move into the 5 string theories, explore M-theory as the grand unifier, check out the rules of supersymmetry, and finally, wrap things up with the geometry of strings.
All right, part 1, the fundamental objects. Before we can even think about building a theoretical universe, we've got to understand our raw materials, right? Every particle, every force, and every interaction we know ultimately boils down to these foundational entities.
It's actually pretty wild how we move from a simple one-dimensional concept to these highly complex structures. We start with your basic string and its massive, universe-spanning cousin, the cosmic string. But then we level up to branes. You can kind of think of them as multi-dimensional membranes. We even get these super-specific variations called D-branes. So modern string theory? It's definitely not just about tiny loops of thread anymore. It's this whole massive ecosystem of multi-dimensional surfaces interacting with one another.
Moving right along to part 2. The 5 string theories.
Thinking about how this math evolved over time is just fascinating. We start with that early foundational work on basic strings and cosmic strings. But then, the field is hit by 2 massive conceptual explosions, historically known as the first and second superstring revolutions. And each of these phases radically expanded just how complex our theoretical map had to be.
So under the umbrella of perturbative theory, the math really branches out. From the older bosonic string theory, we get several distinct flavors of superstring theory following those revolutions. You've got type I, type 2A, type 2B, and heterotic strings. And honestly, for years, physicists were just stuck. They were staring at these 5 competing, perfectly mathematically sound descriptions of the universe, scratching their heads and wondering which one was actually right.
Which brings us to part 3, M-theory, the grand unifier. Now, you might be wondering, how exactly do type 1, type 2, and heterotic strings all exist in the same theoretical universe? I mean, if they're all supposedly the theory of everything, how can 5 totally different versions all be correct at the exact same time?
Well, the massive breakthrough happened when we compared our initial theories with non-perturbative mathematics. This is where we get S-duality, T-duality, and U-duality. You can basically think of these dualities as mathematical bridges. They proved that under certain transformations, one type of string theory translates perfectly into another. So they aren't competing theories at all. They are completely inherently linked.
And this is the grand twist of our whole detective story. All those different string theories, type 1, type 2, heterotic, they're actually just shadows or different perspectives of one massive, overarching framework known as M-theory. The dualities proved they were literally all just parts of a much larger whole.
All right, part 4, the rules of supersymmetry.
Here's the catch, though. To make M-theory and superstrings actually work, traditional math just doesn't cut it. We need a whole new category of supermathematics. We have to expand standard algebra into these wild, complex systems. Things like superalgebra, Lie superalgebra, and superconformal algebra. This totally transforms how we view space into complex superspace and supermanifolds, all governed by these new supersymmetry rules.
Okay, I have to admit,
When you hear a roster of names ranging from the axino and the gaugeino to the higgsino and neutralino, all the way to the stop squark and the superghost, it honestly sounds less like standard physics and way more like a superhero team-up. But what's really happening here is that supersymmetry dictates every known particle in the universe has a heavier superpartner. It essentially doubles the ingredient list required to build our reality.
And it goes even further because these superpartners operate within various models of supergravity. We start from our familiar 4 dimensions, like pure 4D n=1 supergravity, and scale all the way up through type I and type 2 supergravity, culminating in this absolutely mind-bending 11-dimensional supergravity required by M-theory. Literally, gravity itself gets a supersymmetric upgrade to make the math work.
Finally, Part 5, the geometry of strings.
This brings up a massive conceptual hurdle. Why 10 dimensions? I mean, we only experience 3 spatial dimensions and 1 dimension of time, right? So why does this beautiful theoretical map completely fall apart unless the math is calculated in 10, or in the case of M-theory, 11 dimensions?
Well, the answer lies in the geometry of the world sheet, specifically in concepts like Kaluza-Klein theory and compactification. Think about looking at a power cable from really far away. It looks like a flat 1D line, but when you get right up close, you see it actually has 3D thickness. These geometric concepts propose that those extra dimensions aren't missing, they're just curled up or compactified so tightly at the microscopic level that we literally can't see or interact with them directly.
And they don't just curl up randomly either. They take the shape of incredibly complex, Ricci flat spaces, which we categorize into exotic structures like the Calabi-Yau manifold, the hyperkähler manifold, G2, and spin-7 manifolds. The crazy part is, the precise microscopic shape of these hidden manifolds actually dictates the exact physics, particles, and forces we experience out here in our massive macroscopic world.
So when we step back and look at the sheer scale of all this, from one-dimensional strings and multidimensional brains to U-dualities and 11-dimensional supergravity, we really have to ask ourselves something. Are we finally closing in on the true source code of reality? Or, by inventing superghosts and Calabi-Yau manifolds, have we simply spent decades building a breathtakingly beautiful, mathematically perfect map of a universe that doesn't actually exist? It's the ultimate question at the frontier of theoretical physics. And honestly, it's what makes diving into this stuff so incredibly fascinating. Keep questioning, keep exploring, and thanks for joining me on this explainer.
All right, welcome back to the Explainer, everyone. Today, we're diving headfirst into one of the most fascinating and, let's be honest, complex ecosystems in modern physics, string theory. We're going to zoom way out, look at the big picture, and try to map out the entire architecture of our universe, right from the ground up.
So, I want you to start by just completely resetting how you picture the fundamental building blocks of reality. Ask yourself, what if the universe just isn't made of dots? For the longest time, our standard models of physics totally relied on these elementary point particles. But today, we're exploring a massive paradigm shift into a completely different geometry of reality.
Okay, let's really dive into this. If we take our traditional zero-dimensional point particles and replace them with physical, one-dimensional extended entities, which we call strings, literally everything changes. And you might be wondering, why does a simple dimensional upgrade matter so much? Well, because when these one-dimensional strings evolve and interact according to the rules of quantum mechanics, they automatically describe quantum gravity. That is the absolute holy grail of theoretical physics, and it naturally arises just by stretching a point into a line.
To wrap our heads around this giant topic, here's our roadmap. 1. Fundamental objects. 2. Perturbative theory. 3. Supersymmetry. 4. String duality. And finally, 5. M-theory.
Starting right off with number 1, fundamental objects.
Basically, a string is exactly what it sounds like, a fundamental, one-dimensional, extended entity. Whether we're talking about a basic string, a cosmic string, or even when it's expanded into a membrane, or a brain as physicists call it, this is ground zero. By replacing that zero-dimensional point particle with a 1D object, physicists suddenly had a foundational theory that organically evolves to include quantum gravity. It is the ultimate seed from which the rest of our incredibly complex universe grows.
Moving on to number 2, perturbative theory, specifically heterotic strings.
So what on earth is a heterotic string? Well, the word heterotic literally just means hybrid.
It combines the properties of a superstring with a bosonic string, but there's a strict rule here. Every single heterotic string must be a closed string. Think of it like a tiny, vibrating rubber band. It has to form a loop. It actually can't be an open string with loose ends, because the left-moving and right-moving excitations traveling along the string have a completely different character, which makes it impossible to define boundary conditions that would somehow relate them. For those keeping track of the math, there are two primary supersymmetric kinds of these strings, usually abbreviated as HO, which stands for SO32, and HE, standing for E8 times E8.
And this brilliantly illustrates how theoretical breakthroughs actually happen, through intense collaboration. Heterotic string theory was first developed back in 1985 by a team affectionately known in the physics community as the Princeton String Quartet. We're talking about David Gross, Jeffrey Harvey, Emil Martinek, and Ryan Rohm. Their key paper was a total game changer. It was one of the major driving forces that fueled the first superstring revolution, completely changing the trajectory of modern physics.
Which brings us to part 3, supersymmetry.
Now, supersymmetry predicts a partner particle for every single particle we currently know of in the standard model. Why do we even need this? Well, practically speaking, this symmetry helps explain why particles have mass in the first place. But within the specific world of string theory, it acts as an absolutely crucial theoretical patch. Without supersymmetry, the mathematics of superstrings simply wouldn't function at all. It's basically the vital glue holding these advanced perturbative theories together.
Let's move to our fourth point and see how this all builds: string duality.
This is where things get truly mind-bending. The specific duality we're looking at is called T-duality, which is short for target space duality. It was first noted by Bala Sathyapalan in a somewhat obscure paper back in 1987. T-duality basically states that two seemingly completely different physical theories, whether we're talking quantum field theories or string theories, are actually perfectly equivalent. Every single observable quantity in one description perfectly matches a quantity in the dual description. It's like finding a hidden mirror world embedded in the math.
Now, what's really interesting here is how we visualize this. Imagine a string propagating in a space-time shaped like a circle with a specific radius, let's call it r. In this scenario, the string's momentum takes on discrete values. T-duality tells us this is mathematically equivalent to a string propagating in a space-time circle with a radius of 1 over r. In that inverse dual reality, the discrete momentum from the first scenario is exactly equal to the number of times the string winds around the circle. We call that its winding number. It's a perfect mathematical mirror reflecting the exact same physical truth, just from two incredibly different geometries. No way, right?
And finally, we arrive at step 5, M-theory.
To really understand M-theory's impact, we kind of need to look at the timeline. In 1985, as we talked about, the Princeton String Quartet introduced heterotic strings, and that kicked off the first superstring revolution. For a whole decade, physicists explored these concepts, but they ended up with several different, competing versions of string theory. It was a bit of a mess. Then, in 1995, Edward Witten delivered a groundbreaking lecture introducing the M-theory framework, and that effectively sparked the second superstring revolution.
So the crucial point is this. Before 1995, physicists had type I strings, type II strings, and the heterotic strings we explored earlier. They all seem like separate, disconnected theories. But Edward Witten came along and showed that actually they weren't entirely different things at all. They were just different perspectives of the exact same underlying reality. M-theory acts as this ultimate umbrella, beautifully uniting all these disparate superstring variations into one cohesive, masterful map of the universe.
We've scaled all the way from a simple one-dimensional string up to a grand unifying theory of reality. But, the beauty of physics is that the map is never really finished. If M-theory can so beautifully unify these hidden realities, literally showing us that a string's momentum in one dimension is a winding number in another, what other unimaginable equivalences are just waiting to be discovered? Keep that question in the back of your mind as you continue to explore the architecture of our universe. Thanks for joining me for this explainer, and as always, keep learning.
Like what you shared.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.